get into our second example of our discrete Fourier transform, and we are going to look at the signal type here. So this is time in milliseconds, and we are going to create our frequency spectrum of f and our y, our Fourier series. So that's our goal of this function, example today. So let's go ahead and look at what we're dealing with here. So I have my oscilloscope. I can kind of see this signal, and to me, this looks like periodic. And it's periodic from this point, which is 1, 2, 3, 4. My fifth data point here, all the way 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. And 28, 29. So to my 28th data point right here, then I repeat. So from 5 to 28, that's what I'm working with here. Or you could include that last data point, but again, it repeats over essentially that period. So that is what we're going to be working with in this example. So let's go ahead and analyze our signal. And actually, we could choose basically this period. We could choose to the 29th, but let's go ahead and stick with 28. So let's go ahead and analyze our signal, looking at our graph here. So these are my points. I'm going to create my time data by times 10 to the minus 3. This is my RDAT, my TDAT. If I transpose that, I get this plot here. So I want to grab, again, basically all my coordinates from here, my fifth data point, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So I could go all the way to 28. So it's going to be, then I could calculate my value. So one other thing that you could notice, so let's look at our TDAT right here. So let's define kind of some of these values. So what's my time interval spacing? So we know it's in milliseconds. So let's do differences. I want to get this, and that's going to be my mean. So my T delta. So T delta, or my delta T. My delta T is going to be this in seconds. So if I know my delta T, I know my F sub S is equal to 1 divided by delta T. I could do my length of my DAT, that's what I'm going to be working with, is 24. So perfect. So now I'm going to do, that is going to be equal to my big N. I also know that if I have my big N, I could do my T. So my period T is going to be equal to big N times delta T, 24 milliseconds. Again, matches what we have there. I know that my F Nyquist and YQ is equal to Fs divided by 2. I also know that my delta F is equal to 1 over T. So let's go ahead and see if that matches on our notes. Okay, period of 24 milliseconds, great. N equals 24. Delta T is 1 millisecond. So my F sub S, let's double check that. 1000 hertz, great. I know my Nyquist is 500, and that's going to be, and my delta F is approximately 42 hertz, but we could be exact in Mathematica. Excellent. So now all I need to do is just calculate my A sub N's and B sub N's. So instead of length of DAT, I'm going to substitute for big N. And again, it's just our usual function that we did last time. You can go back and look through the other video to kind of see how this code was written. You really want to know how this code works, so you could kind of be sure that you're working with the right data set. But yeah, that is what we're going to be working with here. Begin. I just want to put it into a more kind of common notation. Begin divided by begin. Begin. And let's see how we're working with here. All right, matches what we have previously, which is great. So I have my A sub N's, my B sub N's. Now I'm going to multiply, again, first harmonic times all the way to my Nyquist frequency. So I should basically have a frequency at 41.667, and the last frequency should be at 500 hertz. And, yep, my Nyquist frequency, and here. And again, remember, if I didn't stop at n over 2, if I went all the way to, if you get a frequency spectrum that looks like this, where there's mirror symmetry, and if it's beyond your Nyquist frequency, that's always a good check as well. If I see a plot like this, actually I need to go from 0, excuse me, in order to kind of see from here to here to here. Now I see this mirror symmetry pop up, but we don't want that. We want just do our Nyquist and then end it. That's it. So divide by 2. Let's get our nice values back. This is my frequency spectrum. So I can see that my lowest, my fundamental frequency, my lowest non-zero or trivial frequency is going to be 41.66, just like we anticipated. That's also my dominant frequency, and my maximum frequency is just my Nyquist frequency of 500. That's it. So in order to get our Fourier series, we need to get, again, our A naught, which is equal to 2 divided by big N. And then we just have the total. Let me just take this here. Total here. So, except here, we're not substituting N for anything. In fact, all we're doing is setting N equal to 0. And we should get this function. So, Ry sub t is just A naught over 2. You can see that that's the equivalent of this function right there. And so here's my y's, my Fourier series. And now we can just plot. And when we do that, we have this error here. Well, let's look at what we have. So this is our periodic function. Let's look at the full one, transpose. So this function is periodic. But again, our Fourier series starts from a t of equal to 0. So you can see here that our data here does not start at t equals 0. And actually, we calculated it for t equals to 0.001 was our first data point that we looked at way back here in this data set. So we need to normalize. So we need to start minus 0.04 because I want to make this to be basically the same data set that we're looking at previously. If we plug that in here, now it seems to match fairly well. So that's all we did. We just have to renormalize here, start at this first data point from where we were looking at. So we're not starting at that time equals 0. We're looking at that 0.001. So we're just shifting our data set so that it matches with our Fourier analysis. So that's all we've got here. So this is your second example for Fourier. Again, you could have chosen a larger period and done this analysis and basically got that same function. But again, we want to choose the shortest period. So this function is periodic from here to here. So we want to plot just starting from there all the way to there. And that's it. So I will see you all next time in the next video, and we are going to get into some mechanics. So there might be some more examples coming out soon, some for discrete Fourier transform, specifically some examples about signal aliasing and spectral leakage. So be sure to kind of look over those. But as you can see, we matched basically our frequency spectrum here, and you can look at the Fourier series right here. So before we leave, the biggest kind of piece of advice I could give you for discrete Fourier transforms and to accurately sample a discrete signal, first step, estimate the highest frequency of a signal. So hopefully we know that, or there's some information in the problem or what we're studying that we can figure out what is the highest frequency of our signal. And once we have that information, we are going to try to make sure that f sub s is more than twice as large as that frequency of the signal. Or if you're forced to pick a Nyquist frequency that's less than the highest frequency of your signal, use a low-pass filter to block the frequencies greater than the Nyquist frequency, and so that way that those higher frequencies will not be aliased in your results. Additionally, you could just try, if you don't know anything about the frequency of your signal or what the maximum frequency is, you just set f sub s equal to the f max of your DAC and do the same procedure. Choose a low pass filter to block the frequencies that are greater than the Nyquist frequency once you choose your f sub s. And finally, when you're analyzing a discrete Fourier transform, or you're trying to figure out to accurately sample to avoid signal aliasing and spectral leakage, you need to estimate the lowest frequency in your signal, or estimate the frequency resolution needed to accurately resolve frequency components in your signal, and choose the number of points in to yield the desired frequency resolution. So that's it. So follow these 3 steps for discrete Fourier transforms, and you could always you will accurately sample your signal as best you can. Again, there's some experimental limitations sometimes that no matter what you do, you're kind of stuck. But either way, you could kind of try to avoid some of these issues of signal aliasing and spectral leakage. So expect to see some problems come up on your exam. 2 of them actually related to signal aliasing and spectral leakage. And yeah, that's it. So next time we are going to get into lecture 8, which I do not have up here yet, but into mechanics. So material science is coming whether you like it or not. So I'll see you all next time. Thanks.